To assess the quality of coal, we have two types of analysis to make. The first one is approximate analysis, which consists of 4 steps. The first one is moisture content. We have here a given scenario wherein a 1 gram of finely powdered air-dried sample taken in a crucible and heated after desiccation till constant weight. In getting the percentage of moisture after the treatment, the loss in weight divided by the weight of coal taken times 100 is the moisture content. So we can see here that from its initial weight, after the treatment or air drying, the moisture will be evaporated. Then the difference in weight will be the moisture content. The second one is the volatile matter content. In our scenario, the dried sample left in the previous treatment is being left in the crucible along with the lid is heated in a maple furnace at about 250 degrees Celsius for 7 minutes and then cooled. It waits after desiccation until a constant weight. Then, after the treatment, the loss in weight divided by the weight of coal sample taken times 100 is the percentage of the volatile matter content. The third one is determining the ash content. So from the given experiments earlier, the residual sample is being placed in a crucible and heated in a furnace at about 700 degrees Celsius for about 1 to 2 hours without lid. Then it is cold left in the desiccator and wait till constant weight. So the weight being left is the ash content divided by the weight of the cold sample taken times 100. Then we have the percentage of ash. And lastly is to get the content or the fixed carbon content. Simply, this percentage of fixed carbon can be obtained by subtracting the total percentage of moisture content, volatile matter contents, and ash content from 100. So the significance of this analysis is that by taking away the latent heat of evaporated moisture content, it lowers the calorific value of coal. Hence, lower the moisture content, better the quality of coal. Similar is the effect of volatile matter content, which escapes unworn, so volatile matter content lowers with better quality of coal. Low volatile matter also reduces cooking property of coal. Ash being non-combustible reduces the calorific value of coal. Ash deposition also causes problem in the furnace walls, and the ultimate disposal of ash is also a problem. So, the higher the percentage of fixed carbon, the higher is the calorific value, and better is the quality of coal. Our next analysis is what we call the ultimate analysis. So in this analysis, we determine the carbon, hydrogen, nitrogen, sulfur, oxygen, and ash content of a fuel. So the first step is to get the carbon and hydrogen content. So in our scenario, we have accurately weighed 1 to 2 grams of a coal sample and born in a current of oxygen combustion by combustion apparatus, whereby the carbon dioxide and water are formed. So the carbon dioxide and water are absorbed by the previous waste tubes containing the potassium hydroxide and calcium chloride. So the increase in weight gives the carbon and hydrogen content as follows. So we have here our chemical reaction. So by combustion, our carbon of the fuel produces carbon dioxide, and the hydrogen content react with the oxygen and form water. So these two byproduct of our combustion is being observed by the potassium hydroxide and the calcium chloride, wherein for potassium chloride, it reacts with the carbon dioxide and produce this compound, while the carbon chloride reacts with the water and produces this compound. As you can see here, we have the molecular weight of the carbon, which is 12, and the final molecular weight when it reacts with oxygen is 44. Same with the hydrogen, which is 2, and when it is in water or a compound of water, it has now an 18 molecular weight, the total molecular weight of this compound. Then, based on this, to get the percentage of carbon, the increase in weight of potassium hydroxide, which is literally the weight of the carbon dioxide, times the factor, we have a multiplier factor, which is 12, which is the molecular weight of carbon, divided by the weight of coal sample, times 44, wherein the 44 is a total molecular weight of carbon dioxide. So by the principle of ratio and proportion, we can get the carbon content of our fuel. Then multiplying this by 100, then we get the percentage. So this same approach is used in determining the percentage of hydrogen, wherein the increase in weight of the calcium chloride is being multiplied by 2, which is the molecular weight of hydrogen, divided by the weight of coal sample times 18, wherein 18 is the molecular weight of water compound times 100. Then we have the percentage of hydrogen. The next element to determine is the nitrogen content. In our scenario, about 1 gram of accurately weighed coal sample taken by this method, which is we call Keshdal's methods. And this coal sample is react with the sulfuric acid and potassium sulfite and being heated. Then it is treated with excess of potassium hydroxide and the liberated ammonia. Then it is observed in non-excess of standards acid solution. The excess acid is back titrated with standard potassium hydroxide solution. So from the volume of acid consumed, N content or the nitrogen content is calculated as follows. So the product of the volume of acid consumed, which is normally in milliliter, and the normality of acid times a factor of 1.4, and all over divided by the weight of coal taken. Then this is the percentage of nitrogen. The next element is to get the sulfur content of the coal. So while determining the calorific value of a coal sample in a bomb calorimeter, the sulfur in the coal is converted to sulfate. So finally, the washing containing sulfate is treated with dilute hydrochloric acid and barium chloride solution, which precipitates barium sulfate, which is filtrated in a sintern glass crucible, washed with water, and heated a constant way. Then, by the same principle and getting the carbon and hydrogen by ratio proportion, the weight of the barium chloride, this is barium sulfate times 32, which is the molecular weight of sulfur divided by the weight of coal sample in bomb times 233 times 100. Then this is the percentage of sulfur. The next one is determining the ash content. So the same process in by the proximate analysis is being conducted in determining the ash content. So the residue being left after the burning of the coal is the ash content. And next one, and the last step, is determining the oxygen content, wherein this is the percentage of oxygen. This is typographical error. This is not carbon. This is the percentage of oxygen is equal to the difference, or when we subtract the sum of the carbon content, hydrogen content, nitrogen, sulfur, and ash. And sometimes, depending on the given the problem, we also consider the moisture content. Then summing up the percentage of those um, factors or content, subtracting it by 100, then we get the oxygen content. So the significance of this analysis is that the higher the percentage of carbon and hydrogen, it increases it means it has a higher calorific value of coal. Then we have a better coal. Then the higher the percentage of oxygen, the lower is the calorific value, and lower is unavailable. So means the desirable amount of oxygen is lower, and we desire for a higher value of carbon and hydrogen. While sulfur, although contributes to calorific value, it is undesirable due to its polluting properties as it forms sodium dioxide on combustion.